Welcome back to ECE 501B. Hopefully coming to a D2L site near you will be homework number 4. That's not yet available, but it's still due in a week. That's the idea, which is the 30th. Our exam will be the following time that we meet, which is a week from Wednesday on the 2nd of October. And we're going to try to have a review session for exam number 1 immediately following class, or maybe we'll take a few-minute break. Next Monday, a week from today, we'll do a review session for exam number 1. That's the plan. What that will consist of, your guess is as good as mine, but we'll see what we can come up with. Today, what I want to do is a lot. I would really like to finish up chapter 3, and you basically did that for your homework assignment. But let's look at this example that we started last time. I think that was part of your built-in homework that I gave as an announcement in class. It wasn't a part of your explicit homework assignment, but I asked you to find a matrix representation where we had different basis vectors for the output space, the W. We'll finish that up. We'll try to quickly go through these matrix properties, matrix addition, scalar multiplication, matrix product, and matrix vector product. We'll sort of quickly go through that. We will look at some results dealing with invertible maps, and maps that are invertible need to be both injective and surjective, and the relationships dimension-wise associated with the input and output vector space is what that means for a map to be invertible. That leads us then into isomorphic vector spaces, or vector spaces that are similar. Then we will introduce this idea of an operator where the input and output vector spaces are actually the same. So you take something from your vector space and map it back into that vector space. That will then be an operator, and we'll be working the rest of the semester essentially with operators instead of this more general notion of a map. And then that specialized into a linear map. Now, if we restrict the output space to be equal to the input space, then we're talking about an operator. And that's where we'll continue then with the remaining chapters in the book, chapter 5, 6, etc., continue with this notion of an operator. Hopefully, well, I don't know if we'll get there, but chapter 5 is where you can be reading ahead. Exam 1 might deal with a little bit of that material from chapter 5. Exam 1 then is 1, 2, 3. 4 is just sort of there. It's a chapter on polynomials. You need to maybe accept some of the results if you're not comfortable, or if you haven't seen those. We won't really go into that, but then we will move into chapter 5. Here's our example that we were dealing with last time when we stopped, and that's a matrix representation of a linear map. And what we wanted to look at is what happens to this matrix representation when the output space, in this case R2, is, or we're using two different sets of basis vectors. Does that impact the matrix representation? And hopefully you're anticipating that indeed that will result in a matrix that looks a little bit different. And it's answering this general question: how do we represent a linear map with a matrix? That's really the question that we're addressing or looking at in this particular case. The first example of creating a matrix to parameterize a linear map is if we have the standard basis vectors for the input and the output. R3 is our input space. Those are just our normal standard basis vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. And I may get a little bit sloppy with vectors and row vectors, column vectors and row vectors, but I'm hoping you kind of understand what I'm talking about. But when we start dealing with matrices, it does become very important as to, are you working with rows or columns or what's going on? With linear maps, it hasn't been quite as critical, but once we get into this matrix representation of these maps and operators, we probably need to be a little bit more careful with how we're representing these vectors. But I think I'm going to try to be somewhat consistent in this development today. The map that we had been looking at in our last time through this was this dimension reducing map, and we're taking XYZ into two coordinates, or a two vector, with this relationship in place. And what we wanted to do was see, is there a way to produce this map with a matrix so that if somebody hands you an arbitrary vector in the input vector space R3, can you multiply it by that matrix and produce this linear relationship that's in parameterized form here? And one way to do that is actually to look at how this linear map takes these associations with the different coordinates in your output map and places those or rewrites those in terms of the vectors that are parameterizing your basis in the output space. And to do that, what I'm trying to show is really with these coefficients, that's just an alpha and a beta, for example, that scale your basis vectors, which in this first example with this problem, they're just our standard basis vectors, 1, 0, and 0, 1, which really translates into these two parameters ending up as A11 and A21, where the second subscript is saying that's going to be associated with this input space vector, the first one, and then the other subscripts, the first subscripts 1 and 2 in this case, are saying how much of a fraction or how much of an amount of these two basis vectors are you going to see in this result. That's what I'm trying to show in black and blue, and hopefully we won't be black and blue after this example. So maybe those weren't appropriate colors. But this is then where this is coming from. If we process this first standard basis vector, V1, through this linear map, we simply are replacing X with 1 and Y and Z with zeros. I'm trying to explicitly show where this 2, 7 is coming from. With respect to the standard basis, that really is telling us immediately what these weightings on the respective basis are in the output space. A11 becomes 2 and A21 becomes 7 by just a direct comparison since they're equal. And we can do the same thing for the other two basis vectors, V sub 2 and V sub 3. And in so doing, we end up with values for A12 and A22, which the second subscript again says that's what the second column of your resulting matrix is really going to look like. That's what your second sort of trial vector that you're using to form this relationship is mapped into. In this case, it's minus 1, 5, the values of y in that parameterized expression for the linear map. And finally, with the third basis vector, V sub 3, we end up with A13 and A23 being 3 and minus 6 respectively. And that then leads to this matrix representation of the map, the linear map T, as a matrix. It's now a 2 by 3 matrix. It has 3 columns, which better be compatible with the number of rows or coordinates in your input vector. It has 2 rows, which better be the same number as the number of coordinates in your output space, which was R2. This is then a matrix which will take a given vector in your input space to the output space when both of those spaces have as their basis vectors the standard basis. Are there questions on that? And I think we quickly wrote that matrix down last time in the lecture. But if we now said, what if we looked at a slightly different set of basis vectors for the output space? And really, these 2 vectors, W1 bar and W2 bar, if you wanted to think about that, your standard basis was the x-axis and the y-axis. If you now rotate that, I shouldn't have said 90 degrees, I should have said 45 degrees. So I was just seeing if I could wake up, and that was with a, oh well, I'll just make it thick to emphasize. Do you see that these 2 vectors, W1 bar and W2 bar, are now going to be effectively like rotating the XY set of vectors through 45 degrees and extend those or scale those by a square root of 2 factor, since we're now going to 1, 1 and minus 1, 1. It's one way of sort of, so now instead of thinking in terms of x and y coordinates for your output space, you're saying how much of this vector that's living at a 45-degree angle in the first quadrant and how much of this vector that's living at 135 degrees or in the second quadrant, how do we parameterize the output numbers that we get from that linear mapping in terms of those vectors? So it's a little bit different in terms of how we are representing our result, but really it gives us exactly the same location in space if we needed to find those particular values. The process is exactly the way that we did before. It's just that the specifics or the particulars now are going to be different. We're now using how much of omega 1 bar do we use? How much weight do we place on that? That's now our A11 bar. And how much weight do we put on the second basis to actually give rise to this number 2 and number 7 in the standard basis? And really all that's asking is it's saying you need to find these 2 variables based on these 2 equations. You can now say the top row, A11 bar minus A21 bar, needs to equal 2, and A11 bar plus A21 bar needs to equal 7. 2 equations and 2 unknowns. We could, if we wanted to, put that into the standard matrix form, or we could simply do this with some back of the envelope calculations where we have our 2 equations shown in black. We can simply add those 2 equations together since we have this nice coefficient relationship on the second one, and if we added the 2 equations, that second coefficient is going to be eliminated from the result, and now we simply have 2 A11 bar equaling 9. Or A11 bar is 9 halves. That says that we need 9 halves of that first vector, which was the 1, 1 basis vector. So we take that 1, 1 and scale it by 9 halves, or 4.5. Then we add to that a particular scaling of the second vector, which is 5 halves. So now we go 5 halves times minus 1, 1, and the result of that head to tail combination of those two vectors should put us at the same location in space as the 2, 7 did in the first basis. So that now I'm trying to emphasize that by saying this vector, A11 bar, A21 bar, in the capital W bar basis is now 9/2 and 5/2. Is that okay? So that we're now taking 9/2 of the W1 bar and 5/2 of the W2 bar to produce this same location. It's the same map, it's just now we have different numbers that represent that linear map. If we do the same thing for the second input vector, which was v sub 2, we can do exactly the same analysis. We'll just have slightly different numbers. And now we need 2 and 3 to represent that same location for v2. And finally, I'm going through this fast. I think the concept or the idea should be clear, and you can sort of just leave space or write this down or look at this later. I hope that it's mainly making sense because I don't want to spend too much more time on this. But then the third vector, v sub 3, maps into -3/2 and -9/2, and hopefully when we put that together, we end up with a completely different looking matrix in terms of the numbers in that matrix that describe exactly the same linear map. Now our map, and if we do have concerns about what our basis vectors are, this notation is what the book is using. It's basically saying this is our matrix representation of the linear map T with input vector space with a basis set of v1, v2, v3. In our case, that was the standard basis. And our output set then follows, and that was this two-dimensional R2 that we had as a basis set, omega 1 bar and omega 2 bar. And that was what I was hoping you would do Wednesday night last week when you got home, just anxious to see what's the difference between these linear maps. And show of hands, how many actually did that. I won't really quiz you for that, but that's what I was hoping you might be thinking about. And that can be compared with this. And you can see that the numbers are quite different between this map in the standard basis for input and output and this second map where the change has been we now have a different set of basis vectors for the output map. I hope then it's clear that it's important with these matrix representations of a linear map to keep track of which bases are being used for the input vector space and the output vector space V and W. Thus, the matrix representation of a linear map, let's say T, that's belonging to this set or vector space of linear maps script L from V to W with an input basis set V1, V2, let's say up to V sub n, and an output basis set W1, W2, let's say up to W sub m, those will be written then as this script M with the linear map T, the input vector space made up of the V's, the output vector space made up of the W's. And that's now how we will denote or label a matrix representation. A lot of times we won't be messing or monkeying with the input vector space basis set and the output vector space. They may just be the standard basis. So when the choice of basis, or when that's obvious, what we're using, then we won't go to all that expense of labeling. We'll just call it script M of T. When the choice of basis is obvious, then we will use the simpler notation M of T. Now what we should realize is what I will try to indicate with this extremely important note. Relative to vectors and maps. We've seen this with vectors. As with vectors, maps have an existence separate from their matrix representation, which that last example hopefully illustrated. It really didn't matter what the matrix ended up looking like, it was still for the same linear map, and it just was based on the choice of your basis vectors. As with vectors, maps have an existence separate from their matrix representation. Choosing different basis actually changes the values, which we've been calling these scalars in this field F. It changes these values in the matrix but it really doesn't change the underlying property that's happening with that linear map, but does not change, let's say, the truth or falsity of any statement about the map nor any physical or physically relevant numerical result. And that's hopefully clear from that previous example. That's why I spent some time with that example, to try to get you to see that even though the linear map didn't change, the matrix associated with that linear map was quite different, or could almost be anything depending on what you've selected for your basis vectors. let's quickly talk about some of these matrix properties, and in particular, let's start with matrix addition. And I'm hoping that all of these are second nature to you. Matrix addition is element-wise. On matrices of the same size. It only makes sense to add matrices that are the same dimensions. Meaning if we added an A matrix, an A11, in the first column down to AN1, and then over to, let's say, A1N. Oh, let's make them different dimensionally, I guess. Let's say that we have M rows and N columns. Then the only matrix addition that makes sense is if we have an A matrix and a B matrix that have the same dimensions. Here we have then a B11 up to a B1N in columns on the first row, BM1 and BMN in the second. And I hope it's clear that with matrix addition, you're simply adding up element-wise these different entries in the matrices. That's matrix addition. If we wanted to worry about scaling a matrix with a number from the field that we're dealing with, or scalar multiplication, that scalar then scales each of the elements in that matrix. So the scale maybe I should say scales values element-wise. So that if we now had C times some matrix, A11, A1N, AM1, AMN, then we simply scale each of those elements by the same scalar C. Which, if we were using the notation that the book has said we use for matrix representations, we would have this script of the sum of two matrices or linear maps T plus S is equal to the matrix representation of the linear map T plus the matrix representation of the linear map S. And this scaled scalar multiplication, maybe I should have written that the other direction, but hopefully you're okay with either way. It's equal left-hand side and right-hand side. We've been worrying a lot with things being closed. Yes, our doors are closed, so we're in pretty good shape. But here we want these operations to be closed, meaning matrix addition is a closed operation and scalar multiplication are closed, meaning we get back into the same field that we started with, or vector space that we started with. And because we're using the standard arithmetic, operations, we get all of the other properties that we're used to having with addition and scalar multiplication. Now we can actually create a new vector space. And that new vector space can actually just be a matrix. And we can say, oh, a matrix actually creates a vector space. Which is, let's say, matrix, m rows, n columns on the field of numbers F. And this is now the set of all m by n matrices with elements of that matrix in this field of numbers F, be the real numbers or the complex numbers. If we're now dealing with this new vector space, which is a matrix, an m by n matrix in the field of real number, or in the field of numbers F, what's the dimension of that? So now if you had a, well, our previous matrix was a 2 by 3 matrix, wasn't it? What's the dimension of that vector space if we viewed that now as a matrix and not as an operator? We could have a unique number independent in each of those 6 locations, couldn't we? And that was then 2 by 3, so m by n. That would be then the dimension of any generic matrix that's m by n. This is now m times n, which is really saying that it takes m times n separate numbers to specify a generic matrix that's m by n in size. Or you could, in sort of the MATLAB terminology, you could vectorize a matrix. You could now stack up all of your columns in your matrix into one vector. And now you have a vector that looks like more like R to the mn. And that would now be your vector space. Or that's the dimension of your vector space. The vector space is this matrix that's mn in size. Now we also, so we've looked at matrix, 2 properties, matrix addition and scalar multiplication. We also might want to multiply these matrices. So matrix representation of a linear map, let's say, multiplication. We've really already sort of talked about this. Before we saw how if we had these two linear maps, we could basically compose those linear maps into two separate sort of operations. Earlier we saw how, in the, let's say, special case, and the reason it's special is because we need the output space of one to be compatible with the input space of the other, or the second map, where we have this linear map T living, let's say, or associated with the linear maps between U and V, and we had a second linear map S that mapped between the vector space V and W, then the multiplication of the maps could be sensibly defined by ST operating on V was the same thing as S operating on TV. And what did we know or say about the general relationship between ST and TS? As far as maps, it makes a difference how you operate on vectors in terms of the sequence or the order with which you operate on those. Meaning ST is not necessarily the same as TS. And if we wanted to, then we could look at how this works with respect to the matrix representations. What would we want to have happen? If we had the matrix representation of this linear map ST, what would we like that to look like in terms of the matrix representations? Hopefully it looks like the matrix of S times the matrix of T, like you're used to seeing. And this actually works fine using the standard, let's say, definition of matrix multiplication. Now, to save you that tediousness, we won't cover that here. I'll assume that you can multiply matrices. if that is leaving you a little bit on shaky grounds, then maybe you should review that if necessary. But what I do want you to be thinking of, how many in here have actually had a linear algebra course? Maybe not as many as I would have expected. So let me just talk about another way of thinking about a matrix product or a product of two matrices. However, another way of thinking about matrix multiplication can be helpful. And by that, let me just say here is an example. I think it's easier to just sort of talk in concrete example terms. Suppose that I said, how about the product of A times B, where A is 1, 5, 7 in the first column, 6, 2, whoops, can't even read my own writing, 6, 2, 1 in the second column, and 4, 5, 3 in the third column, and maybe we want to multiply that by B, which is 1, 0, 0, 2, 0, 1, 0 minus 1, 0, 1, 1, 0, and 1, 0, 2. Here's now A, and there's B. The first question, are these matrices compatible? Do they even make sense to multiply? And to answer that question, we look at the number of columns in A, and is that the same as the number of rows in B? Now, in one way of thinking of this in terms of multiplication is you might look at the columns in B and say, let's look at the first column. That's 1, 0, 0. And if you think about what that's doing, it's really just scaling each of the three columns in the A matrix by the element in that respective row of the first column in B, meaning scale or multiplying AB in the first column, it's really just taking the first column of A and copying it down into the first column of the product of A times B. We're taking 1 times each element in the first column and nothing times the second column and the third column. We're really just writing down immediately a copy of the first column in A. That's what will happen with the product. If we did the same thinking for the second column of B, then we take twice the first column and add to that the third column. So this is just telling us how are we combining the columns in A. We're scaling the first column by 2 and adding to that 1 times the third column. And then that gives you a pretty quick way to write down the answer. The second column in our result will then be 2 times 1 plus 4, or 6. It will be 2 times 5, or 10, plus 5, which is 15. And it will be 2 times 7, which is 14, plus 1, plus 3, which is 17. Is that clear where that's coming from? What about the third column in the product? What does this, what's that going to do then in the product? It's going to take the negative of the second column of A. And the second column of A is 6, 2, 1. We now have minus 6, minus 2, minus 1. And we don't have to worry about looking at, oh boy, what do I have? I have 0 times 1 plus, doing this row column product to do the multiplication. What about the fourth column of the product? That's going to be the first times this, or plus the second, right? So we just add those first two columns and we have 7, 7, and 8. And that's pretty quick to write down. And finally, then the last column of the product is going to be just add the first column plus twice the third. Twice the third will be 8, 10, and 6, and we just add those to 1, 5, and 7. So whatever I just said, I think I had 6 down below and 7 adding to that. I now have 1 plus 8, or 9, and I have 5 plus 10, or 15, and that's now my product of this matrix A times B, and I didn't have to go through all of these different row times column multiplication process, although you could do that and you better get the same result. Question? So now the question was, can I repeat one of those? So this is a process that I'm hoping you start to get comfortable with in terms of if you see matrices multiplied, you might think of what's the intuition behind this. If we simply go back to the second column in B, the second column of B is saying, oh, really what this is saying is take 2, and where is this? This is actually going to be operating on the first column of A. So we take 2 times the first column of A, we take 0 times the second column of A, and we take 1 times the third column of A, and we add those 3 pieces up. We now have 2 times the first column, which gives me 2, 10, and 14, and I add that component-wise with just the third column, which is 1 times the third column, which is 4, 5, and 3. In the first place, then, that should be 2 plus 4, which is 6. In the next place, it's 10 plus 5, which is 15. And in the bottom row of that second column, it's 14 plus 3, or 17. And that's where this 6, 15, 17 is coming from. Meaning, if you now looked at this, you could say, oh, well, whatever's going to happen, I'm going to be living in this space that's consistent with this direction of the first column and some of the third column. And I'm not using any of the direction in the second column of A in the combination that's created by the second column in B. So it's telling me sort of all this is doing over here with this AB product is it's just creating combinations of those columns in A. That's all it's doing. That's the only place you can sort of get to in this result of this matrix product, A times B, is a linear combination of the columns of A. If you wanted to, you could actually look at it just sort of the other way, and you could say, well, if I was living in the row space or row spaces of this AB product, then I would say, oh, you know what? The first row in my result is going to be the first row of B plus 6 times the second row of B plus 4 times the third row of B. And if you did that, you should get this 1, 6, minus 6, 7, 9. So you could look at it in terms of rows also, if you wanted to. That may be a little bit odd, but if you get used to it, it starts to give you a better appreciation for matrix products instead of just saying first row, first column, first row, second column, first row, third column, and going through all of that machinery to come up with the same idea. And that's what I want you to be thinking of is you can think of matrix multiplication to be combining columns, or you could think of it consistently as combining rows. And I guess if you ever get bored, you can sit down and say, well, let me do this matrix product two different ways. First by combining columns, and then I'm going to combine rows. You better get the same answer. Okay? Maybe you'll never be quite that bored to do that. Now this matrix multiplication gives us a couple of properties that we know are true. The standard matrix multiplication maintains the properties we want. One, for example, if we're given an A matrix whose scalars or whose elements are an element of this field that's M, and the matrix A is M by N, and if B is of size, let's say J by N, maybe that was a poor choice of, why don't I do this? Let me make A, well, no, that one I like, M by N. Let's make the other one J by L, just to be different. So B is now J by L. What's the only time when this matrix product is going to be defined? We need the columns in A to be equal to the rows in B. Well, that's only going to, that product will only make sense or be defined when N is equal to J. And that's equivalent to the requirement between the output space and the input space, equivalent to the requirement that the output space of one map must be the input space of the other map. In this case, the output space from B needs to map into the input space of A. So N is equal to J. The other property that we've talked about with the maps is even when we could multiply them A, B, or BA, those products are in general not going to be equal. They don't commute. So even when the multiplications are defined in both directions, in general, this matrix representation of T times the matrix representation of S is not going to be the same as the matrix representation of the linear map S times the matrix representation of the linear map T. Now, we've been talking about matrices, but we could specialize that to a matrix that's just one wide, or just a column vector. We can work vectors into this same framework by defining the matrix representation of a vector as a matrix with a single column, where the elements in that column are the expansion coefficients of the vector in terms of the basis. As an example, suppose that we are given a vector V in, let's say, a vector space capital V and a basis on, let's say, V of, and this may get really confusing, what do we want that basis to be? Why don't we just call it something a little bit different? Let's say U1, U2, up to U sub n. And those are not, so here it should be clear from context what we're meaning. U1 is a column. It's not just one element. U sub 2 is also a column, and it's the same size as the vector V. So if V is 5 by 1, all of these U's are 5 by 1. And those U's are a basis of V. And as a review, what's a basis mean? If the U's are a basis, then U1 through U sub m need to be linearly independent, and they need to span all of this vector space capital V. So that's the basis. And if we have a set of basis vectors, U1 through U sub n, then we can linearly combine those to form any vector V in our original vector space capital V. But the way that we will write that as a column vector is we will simply say, oh, you know what? We need to just order those coefficients, the A's, to be compatible with these expansion coefficients used to rewrite V. A1 is associated with the first basis vector. That's the amount of U1 that's making up V. A sub 2 is the amount of U2 that's making up basis V. Now we can talk about forming not just matrix, but now a matrix vector product. And here's the proposition. Suppose we are given a linear map T that's taking V to W, and now let's say V has a basis. Now this is really going to be, but this is now a new phase. This is now a new proposition. So let me just say the V's are with capital V, and the basis on W are W1, W2, on up to, let's say, W sub n. Now what we want to show is that the matrix representation of V being mapped through this linear map T is actually going to be this represented by the matrix representation of T times the matrix representation of V, which is what we're used to seeing. We now have AV or TV. Well, we don't have a TV in here, luckily, or that's what you would all be watching, right? Not me. But now you can go home and call this lecture up on your TV, and then you can watch TV all evening. That's fine. Okay, that would be fine with me. That YouTube channel, that's a good one, isn't it? All right, so now we have this matrix vector product consistent with what we would expect it to be. Now the proof of this gets a little bit tedious, and that's why you might want to watch this if you're having trouble sleeping tonight or sometime in the future. What's the matrix representation of the linear map T? How have we denoted that? In, let's say, the elements are A's. So now that's just A11, A, let's say, well, did we give it dimensions? So now our output space is M, so we need to have M rows, and we need to have N columns. In A. That's the matrix representation of this linear map T. And if we do that, if we looked at T with individual, so now if we operated on each of the basis vectors in the original input vector space, capital V, we would have N of those, wouldn't we? And we could say, well, let's just parameterize those by this parameter K. So if I want the second column in this matrix vector product, well, this is really now a linear map of how does the second basis vector of V get mapped into the output vector. TV sub K is, how have we written that before? That's now just this sum of A. J was the particular output basis vector. The second subscript was associated with the column on the input vector that we're mapping, and this is now going from J equal 1 up to M output vectors, and this is now times Wj. So that's how we would parameterize this linear map of each of the K. So this representation is for K an element of 1 on up to N, isn't it? This is true, this relationship, for all of those K's, and I can't make a capital K or a lowercase k different to save my soul. So you'll just have to tolerate my poor penmanship. But that's a lowercase k in both cases. Now, what if we rewrite v as, let's say, some linear combination of the basis vectors in capital V? Now, if we map V through this linear map T, that's going to be B1 times TV1 plus B2 TV2, etc., down to B sub n T V sub n. But look at what we just had up above for all of those TVs. We had n TVs, so now you're really confused. You have n monitors to be looking at, right? N Nevada monitors to watch. I'm sorry, that's the TV, I guess. That's not a monitor, is it? So we have TV, and this is now how TV sub k, each of those is parameterized. Now we need to plug this for where we plug in k equal to 1, we would replace this TV1 with this summation symbol with k equal to 1. Does everybody see what I'm trying to do? So that now I can replace this or rewrite this as B1 times the summation j equal 1 to m of a sub j1 w sub j. Plus, I'll just do it one more time at the end, which is b sub n, and this is now this sum from j equal 1 to m of a, what's this one going to be, subscript-wise? I'm worried about the v sub n parameterization, aren't I, or tv sub n, and this is now w sub j. But now I hope you can see that this collection that re-parameterizes TV, I could rewrite. I could say, well, let me just pull out all the different WJs, for example, and now find the coefficient for W1. What's the coefficient associated with W1? Well, I have a coefficient in all n places, don't I? I now have a summation of n pieces for each W1. And I have this, a similar collection of a sum for W2. Meaning I can now rewrite this as this sum from j equal 1 to m of a sub j1 b1 plus a sub j2 b2 on up to a sub jn b sub n times w sub j. But now this entire piece right here is the expansion coefficient for the wj basis vector. So if I wanted the expansion coefficient in a column vector associated with each of these output basis vectors, if I wanted the first one, I would just say, oh, that's a sub 1, 1, b1 plus a sub 1, 2, b2, etc. Meaning, I can now say that TV, well, maybe I should say TV is just the linear map. I want the matrix representation of TV, that's now going to be A11B1 plus A12B2 plus A1NBN. And I could just do that repeatedly all the way down to A sub M1B1 plus A sub M2B2 plus A sub Mn B sub n. What is this beast in this bracketed notation? What are the dimensions on that object? How many rows do I have? M, right? Michigan, the number of output, or the dimension of my output vector, or the number of bases in my output vector space. M. How many columns do I have? That's just the one column, isn't it? This is now just the matrix representation of the linear map T on a generic vector V. So this is now belonging to M by 1 dimensionally, just to sort of make sure that I'm on the same, or thinking about this properly. But now if you looked at that, you could say, you know what, I could create that same combination of A's and B's if I simply looked at the A matrix that I started with and post-multiply that by a column of B's. Because this is now A11B1 plus A12B2. So I'm just reading across the first row of A down the column of B to get my first row. Then the second row, the mth row, would be AM1 times B1 plus AM2 times B2, meaning this matrix representation of this map TV that's equivalent now to A11, AM1, A1N down to AMN times B1, B2, B sub n. And that actually is now this M by N matrix. This is an N by 1 matrix, isn't it? Where both of these, this is now the matrix representation of T times the matrix representation of V. Questions on that? So now we've looked at these different properties. Matrix addition, scalar multiplication, matrix-matrix product, and matrix-vector product. And it's all consistent with the matrix representation that we created to begin with. Now my map that I began the lecture with was overambitious, wasn't it? I didn't get as far as I wanted. I barely got through maybe the second goal on my map. So that was, I may have to do another conversation with myself, and you'll have to watch the lecture to see what we can learn about invertible maps. And once we have a map that's invertible, which means it's injective and surjective, then we can start saying, well, what kind of a matrix would provide us with an invertible map? What are the dimensions on a map if it's invertible? If we had a map A and we multiplied it by its inverse, let's say A inverse, to be compatible, we need A times A inverse to be equal to A inverse A. What's that telling us about the row column behavior of the matrix and its inverse? The columns of one have to equal the rows of the other, and vice versa. The columns of the other need to be the rows of the first. Meaning, how's that going to happen? Well, they have to be a square. So the matrix is going to have to be square. Once we have invertible maps that are one-to-one and onto, meaning we have square maps, now we can talk about vector spaces being similar to one another. If they are connected, or if we can get from one vector space to another by an invertible map, meaning each vector in one can be uniquely one-to-one and onto connected with a vector in the other vector space, those two spaces will be similar or isomorphic. And I may have to give you that lecture off the normal beaten path, and we'll pick up hopefully maybe with chapter 5 on Wednesday. That's the plan. Okay? Thank you for your patience. Homework number 3 is due tonight. Is that right? Okay. See you Wednesday.